In our introduction, we suggested that the most mathematically precise way to define a fraction is as a point on a number line. Focusing on fractions as numbers helps students understand that the mathematical operations that we do with them are identical to those that they know already for whole numbers. But fractions are more powerful than whole numbers because they can represent ideas that we cannot count. For students who have only thought of numbers as a means to count things, the idea of a fraction is a big conceptual leap. Now numbers represent part of something. They may also represent ratios. In fact, the word fraction comes from the Latin word fractus, which means broken. The idea here is that we can break up something that we formerly thought of as a single unit into parts of that unit or other definitions of what a unit is. We will define fractions using a number line. From work in the first or second grade, students should be familiar with the number line that represents the whole numbers as evenly spaced tick marks on a horizontal line. Let's review where this idea came from. We start with a horizontal line and choose some arbitrary point on it, usually to the left, and call it 0. At that point, we pick a second point to the right of the 0, and by labeling this point 1, we have defined a unit. Notice two ideas here that are subtly different. We've defined a length of 1 unit, and we've also defined a point on the number line that is at 1 unit. This point represents the more abstract idea of the number 1. This special segment on the number line is called the unit segment. That's the segment from 0 to 1, and we represent it using the notation square brackets 0, 1, close square brackets. Now the remaining whole numbers can be defined. They are the locations on the number line that fall at full multiples of the unit segment. So for example, if we move two of these distances, the unit segment distances from 0, we get to the whole number 2. If we move 3 lengths, we get to the whole number 3, and so on. Incidentally, one can move to the left of 0 in this same manner and define negative values and the integers. Notice now that any segment that has a length that is an integral number of unit segments, say from A to B, this length is a multiple of the unit segment. This is an idea that we use when we add and subtract numbers on a number line. We should stress to students that the physical length of each segment in the number line is unimportant. 1 unit is defined by whatever distance is chosen from 0 to 1. By extension, we can see that 1 unit will be the distance between any two whole numbers on the number line. So let's move on to fractions. One can imagine breaking the unit segment into, say, 5 equal parts. Let's focus on this first part here. Again, two ideas are defined. One is the location of that point, and the other is the length of the segment. Clearly we can't call that location 1. We've already defined that as our segment. So we have new notation that we need to bring in, and that is the notation 1/5. We will use that name to define that point on the number line, and it also defines, therefore, this segment, the length of that segment, just as we did with the whole numbers. And now, in a similar way, we can look at the full multiples of this distance and give them names that represent multiples of a 5th. We'll call this position here 2 of those, or 2/5. Over here we have 3/5, 4/5, 5/5, and so on. And in fact, we can keep going by continuing our subdivisions of 5 parts for every whole unit and have fractions such as 6/5 and 7/5 and so forth. And 10/5. Notice that using this notation, we've actually defined new names for numbers that we already had. For example, we now have 5/5 as another name for the whole number 1. Likewise, we have 10/5 as a new name for the number 2. We can take it one step further. Don't forget 0/5, another name for 0. So in this example, we had broken the unit segment down into 5 equal parts, and we called that segment 1/5. But there was nothing magic about choosing 1/5. In fact, let's suppose that we break the unit segment down into n parts. I've included a little squiggly mark to show that I'm not sure how many segments fit between 0 and 1, but if I choose to break the unit segment into n parts, then the notation that I'll use to represent the first mark, the first segment, is 1/n. If I double that length, I have 2/n, which represents the next point. I can triple that length and get to 3/n, and so forth. Now at this point I don't know how many segments are located in this break, but I do know that by the time I get to 1, I have to have created n segments, each of which is 1/n in length. I can continue going. This would be the next segment, one more multiple of 1/n. That would be called n plus 1/n, n plus 2/n, and so forth, all the way till I get up to the number 2. And by the time I get to 2, I will have had n segments here and another n segments there. That's 2n segments, and each of those segments is a 1/n, so I'll have 2n/n segments by the time I get to there, and this would be another name for the number 2. So from this, we can generalize the equivalence of whole numbers and fractions if we introduce one more symbol. If we let m be some whole number, any whole number, then m times n will be the number of segments in n whole numbers. Here's one whole number, two whole numbers. If we go up to m of those, each of them has n segments. We'll have m times n segments, and each of those segments is a 1/n segment, and we get that this expression, m times n/n, will be the same as the whole number m. Let's highlight that one because it's an important result. There we are. And probably the most common use of this fact is when we notice that 1 is equal to n/n. Any whole number over itself as a fraction represents the whole number 1. I should point out that for the purposes of this discussion, we have limited ourselves and should be aware that we're talking about n greater than 0. So, in short, a fraction is a number that is a multiple of the number 1/n that we define by breaking the unit segment into n equal parts. So you may notice that by breaking the unit segment from 0 to 1 into smaller and smaller and smaller subsegments, we can fit an infinite number of numbers between 0 and 1. So you may be tempted to conclude that there are no other numbers except for whole numbers and fractions. However, the Pythagoreans, you remember the Pythagorean theorem named after Pythagoras? They knew in the 5th century BCE that the length of the diagonal of the square, whose sides was 1, was a number that could not be written as a fraction. These are called irrational numbers, and our study of them will have to wait for another day.